Okay. So supposedly.
Yes, I think we can start.
Okay, so are we recording or not? Okay. Okay, welcome again. So this is the second lecture of the course on inverse semigroups, groupoids, and Steinberg algebras. Today, the references for today's lecture are those that you can see there. We will still make reference to Excel's monograph and also a recent paper by Abdelatif, Clark, Jansen, and Marsland, which I will refer to as Abdelatif. Yeah, that's where the snakes in the title come from. And then Steinberg's seminal paper on Steinberg algebras of groupoids. Okay, so let me recall from last time that if we have an inverse semigroup and sitting inside S, we have E, the idempotent elements, and we have a locally compact T2 space X, and an action. Then we write the S for the domain of theta of S, which is the same as the domain as S star S. And then the transformation groupoid of the action is the quotient of the pairs Sx with X in the domain of S by the equivalence relation, so that the class of a pair Sx is equal to the class of a pair Ty if and only if X is equal to Y and there is some idempotent P, so that X is in the domain of P and Sp equals Tp. If we have an open subset U in the S, we write S bracket SU bracket for all the Sx with X in U. And well, we write together several facts that are proved in Excel's monograph. If we have a basis of X, then the sets of a form SU with U in the basis form a basis of a topology that makes this groupoid an étal groupoid, and the SU are open bisections for that structure. And every étal groupoid arises in this way. Okay, so that's all for the recollection. Now, let me go to the blackboard. First, so last time we saw the general construction of a transformation groupoid of a semigroup acting on a space. And now I want to make a couple of concrete examples. So a directed graph consists, which we will call E, consists of two sets, E1 and E0, and maps R and S. The elements of E1 are called edges. The elements of E0 are called vertices. And if I have an E in E1, then I regard it as a little arrow that departs from S of E, which is the source, and lands in R of E, which is the range of the edge E. Okay, we will assume for simplicity that E0 and E1 are finite, and that every vertex emits at least one edge. Okay? Okay. And so I have some further space here. Let me use it. I write PE for the sequences E1, En, with n greater than 1, and so that REI is SEI plus 1. These are the paths. P is for paths. And a path that involves n edges is a path of length n, which we denote like the module bars, okay? And we also add to this the vertices, which we regard as paths of length 0. All right. And then we consider XE the set of all infinite paths. On E. Okay. So this will be, we will give this set a topology, and this will be the space of which our semigroup will act. So we first give a topology here. So for each alpha in PE, we consider Z alpha, which is of the form, all elements of the form alpha X, where X is in XE, and the source of X equals the range of alpha. So that this is again a path, an infinite path. So these elements of Z alpha are paths that begin with alpha. Okay? So one checks that, these are the Z alpha with alpha in PE, form a basis for a topology making XE into a Boolean space. So it is compact, and it has a basis of compact open subsets, which are these ones. The Z alpha are Klopen. So this is in addition, so it's a compact Hausdorff space, and the Z alpha are compact and open. Okay. La pantalla. Por eso necesitas el... All right. No, eso se saca con eso. No, bueno, pero a mí me molesta, me da sombra acá. Y eso seguro que si yo escribo acá... okay. So sorry for this. So I just defined the space. No se puede ver el pizarrón de arriba. Pero no se toca ahí eso. Ah, sí, es ahí. Okay. Thank you. So I defined the space, and now I want to define a semigroup. The semigroup consists of all elements alpha. Alpha is a path, and beta is a path. And the range of alpha equals the range of beta. union 0. Okay, so how do I multiply this? So if I have alpha 1 and alpha 2 paths, and the range of alpha 1 equals the source of alpha 2, then alpha 1, alpha 2 is the concatenation. And if R of alpha 1 differs from S of alpha 2, then alpha 1, alpha 2 is 0. And similarly, if I have beta 1 star, beta 2 star, then I define this as beta 2, beta 1 star, where, of course, 0 star is 0. Okay, so if this is 0, then the result is 0. Otherwise, that is, when the source of beta 1 is the range of beta 2, then this is just the concatenation. And so this is the start of the concatenation. And now I had to tell you how I multiply the beta stars times the alphas. So if beta is smaller than alpha, so what do I mean smaller? So beta is longer than alpha because it's alpha and perhaps something else at the end, right? However, if I think of the elements of E1 as letters, then this alpha beta 1 comes first in the dictionary. Alpha comes first in the dictionary than alpha beta 1, right? So I write, in this case, I say that alpha is bigger or equal than beta. So in this case, this alpha that sits inside beta, when I start it, I get beta 1 star, alpha star. Alpha star, alpha is the range of alpha, and therefore we get beta 1 star. So this product is beta 1 star in this case. Now, what happens if beta is bigger than alpha? Then this means that alpha is beta times some alpha 1. So in this case, I get alpha 1. And otherwise, beta and alpha are not comparable. And in that case, I get 0. Okay, so you can check that with these prescriptions, you get that SE is an inverse semigroup, and that what's the inverse? Well, as you can imagine, the star permutes the factors. Okay, so we let SE act on XE as follows. So what does alpha beta star do? So first of all, what is its domain? It's the Z beta. Recall that Z beta is the set of all infinite paths that begin with beta. And this will land in Z alpha. What does this do? So it takes beta x, it removes the beta, and adds the alpha. This is what it does. Right, and notice that if this is y and this is z, then the length of beta plus I letter of y, so this would be the ith letter of x, is the same as the length of alpha plus I letter of z, because, again, that's the ith letter of x, right? And well, one can show as an exercise that SE cross XE is in bijection with the set of all pairs Y, K, Z, such that there exist M and N bigger or equal than 0, so that K is M minus N, and Ym plus I equals Xn plus I for all I bigger or equal than 1. And the bijection sends the germ alpha beta star beta X goes to alpha X degree length of alpha minus length of beta, beta X. Okay, so one can, the exercise is to check the bijection, find out what the topology, so once you have a bijection and you have a topology here, you can translate the topology here, making this into a homomorphism, and then check that this one is Hausdorff. So in this case, you get a Hausdorff groupoid. Now let's see an example of a non-Hausdorff. So that groupoid is again ample, the groupoid we just mentioned, because it is étal, and this space of units of objects is this XE, which we said was Boolean. Okay. So another example is the two-headed snake. And so you could, so this is taken from De Latif et al. Section 3.1. All right. Right. So consider this graph. So it's a graph with only one vertex, and two loops, two edges. And let X be XE. Right, so what is XE? It consists of all words, all infinite words, on A and B. So, for example, one such infinite word is A infinity, which is you repeat A infinitely many times. So I will call this A infinity. Okay. So I will have a groupoid G with G0 will be X. And G1 will be X, disjoint union, a mysterious element psi. And then I will have domain and codomain and identity maps. The identity of X is just X, which is also the domain and the codomain of X, whereas the domain and the codomain of psi is A infinity. And what else? Well, and then since the x's are identity maps, so you can only compose two of them if they correspond to the same object, and x times x is x. So, and once I told you what the domain of xi and codomain are, you know how to multiply xi by an object, right? By the identity of an object. So all that remains to be said is what psi times psi is, and we define this to be infinity. Okay? So you can check that this is a groupoid. So the only invertible element, I mean, the elements, the x's, have as inverse themselves. And this tells you that also psi is its own inverse. Right, so I now have to give a topology. And so recall that on XE, we had this topology for any path alpha, which is any word alpha. And now, in particular, one of these is for n bigger or equal than 1, I have Z alpha n, which is an, which is the strings of the form ans with x in C. This condition is not necessary since there is only one vertex. Okay? Then I will add Z A n tilde. This will be Z A n, from which I remove A infinity. So clearly A infinity is here. And instead of A infinity, I add psi. Okay? So one checks that the Z tilde an with n bigger or equal than 1 union of the Z alphas with alpha path in E, which is just any word on A and B, this is a basis for a topology on G, making it into an ample groupoid. Now, this groupoid is not T2. Why is it not T2? Because you cannot separate A infinity from this mysterious element psi. Every open neighborhood of psi contains A infinity. So there is no open neighborhood that contains psi, and there is no pair of open neighborhoods, one containing psi and the other one containing A infinity, that are disjoint. Yeah. Okay. So if you like this, in this paper, you can find a three-headed snake too. Okay. So we've given examples of groupoids, Hausdorff and non-Hausdorff, both ample. And now to an ample groupoid, we want to associate an algebra, the so-called Steinberg algebra. And before we go into that, we need to talk about locally constant functions on a weakly Boolean space, which is my next topic.
Okay. So functions on weakly Boolean space. We take K will be a discrete commutative ring with unit. Okay. So X and X will be a weakly Boolean space. The set of all functions from X to K, we denoted K power X. And, right. So this is too big. Inside of here, we take, so this is a K module with operations pointwise, defined pointwise. So in these K modules, we take the sub K module generated by the characteristic functions. So this is the characteristic. Function. Of the compact open subsets of X. Right? So notice that our hypothesis that X is weakly Boolean says that these U's, the compact open ones, form a basis of the topology, right? So if you take a nice space X, then this set might be empty, okay, or have just a characteristic of the empty set, right? But so that's why it's important that X be. You can always consider this for any space X, but it's interesting only when X is at least weakly Boolean. Okay. So, for example, if X is T2, then, so, and this set I will call CC of X. This little c stands for compactly supported, and the big C, well, it should mean continuous, but there's a caveat with this. So if X is T2, then CCX honors its name in that it consists precisely of all the continuous compactly supported functions. So clearly, if X is T2, besides being weakly Boolean, so if X is generalized Boolean, then any compact subset in X is closed. So these U's, since they are compact and open, they will be clopen. And so the identity map, or the characteristic function of a clopen subset is always continuous. And so these things do live here. So that's, this inclusion is clear since compact impera is closed because X is assumed to be T2. For this inclusion, you take your, you can write the space X as the union of the inverse images of all the lambdas in K. So this simply says that phi takes some values, right? So any x is assigned some value by phi. Now, inside here, so since phi is continuous and k is discrete, each of these is cloped. So because the lambdas are cloped. So the set of where phi is non-zero, which is closed because k is discrete, this is what, whether phi is continuous or not, we will refer to this as a support of phi. So it's always the open support. It need not be closed in general, but if phi is continuous, it is closed. So this is the union for lambda non-zero of phi minus 1 of lambda. And since this is supposed to be compact, since phi is continuous and compactly supported, then here, this has to be the union for some lambda in F, finite, of phi minus 1 lambda, which means that phi is the linear combination for lambda in F of lambda times the characteristic function of this set phi minus 1 lambda. And this set phi minus 1 lambda is cloped and sits inside the compact subset, so each of these is compact open. Therefore, it lives in here. Okay? So for continuous, when the space is X is Hausdorff, then this CC, as I defined it, coincides with the set of all continuous compactly supported functions on X. But this two-headed snake provides a counterexample. So in the general case, if X is not Hausdorff, so in this case, X is not called X by G, but G. So G, the two-headed snake, then the characteristic function of Z tilde A minus the characteristic function of ZA. So recall that Z tilde A and ZA had all the same elements, except that whereas this one has A infinity and doesn't have psi, this one has psi and doesn't have X infinity. Right? So this boils down. So this function phi satisfies that the support of phi consists only of psi and A infinity. And this, the interior of this, is the empty set. So if phi were continuous, its support, defined as the inverse image of the non-zero elements, should be open. Not only this one is not open, but its interior is empty. Okay? So so this one lives in CC G and is not continuous. Right. So Okay, so never mind that. So what example of a weakly Boolean space am I interested in? Well, recall that if G is ample, then it's étal, so it's locally homeomorphic to its unit space, and its unit space is generalized Boolean. So G is weakly Boolean. So it makes sense to consider the CC of G. And we have the following proposition. This is in Steinberg's paper as proposition 4.3. So suppose that G is ample, then CCG is spanned by the characteristic function of the compact open bisections, right? So by definition, this is spanned by the characteristic functions of all compact opens. And the proposition says that, moreover, this smaller subset, the compact opens, which in addition are bisections, already suffice to generate this K module. And let me give you a proof of this. So certainly, this lives in here. And can the camera take that? And as you can see up there, the left-hand side of this proposed identity is generated by the characteristic functions of all compact opens. No, acá. Bueno, sigo acá. Okay. So what we have to prove is that if U is compact open, then the characteristic function of U is in the span of the characteristic functions of V const. Okay? So what do we know? So we know that the compact open bisections, because G is ample, the compact open bisections form a basis. And so, and U is compact and open. So there exist B1, Bn compact open bisections, so that U is the union from I equal to 1 up to n of V of the Vi. Okay. Now put this symbol to mean the first 10 natural numbers, which are the indexes of my union. Okay. Then for each non-empty subset I of n, consider Vi to be the intersection for I in I of the Vi's, from which we have removed the union for all the j's not in I of Bj. So these are the elements that are exactly in all the VIs and in nothing else, and in no other of the VJs. Okay? So clearly, U is the disjoint union of the VIs. Non-empty and inside here. Okay. Now, and here is the important point. U is compact open. So the VIs are closed because U is compact and the VIs are compact too, and U is compact implies compact in our vocabulary. The VIs are closed in U, besides being open. Yeah, this is what I said. In our vocabulary, compact implies something. Okay, so the VIs are closed and open inside U. So the intersection of the VIs is closed inside U. And since U is compact, this is compact. Now I removed from this compact subset a union of open subsets. So I intersected, in other words, I intersect this with the complement of this inside U. And so I intersected with some closed subset. So this is again compact. And it is open because this is a finite intersection. And this union that I just said was closed, was open, is also closed. Right? So this is again compact open. And the fact that the domain and codomain functions are injective does not change when we restrict here. So these are also bijections. Okay. So what does this mean? This means that the characteristic function of U is the sum of the characteristic functions of the VIs. And this is in the span K of the characteristic functions of the compact open bisections. Okay, so here it is important, it is very important that all the VIs sit inside U and the U is Hausdorff. Okay, I cannot do this without this hypothesis because the intersection of compact subsets in a non-Hausdorff space need not be compact. Okay, right. So, yeah. So far, CC of a space is just a K-module. And in the case when G is when the space is an ample groupoid, the groupoid has a product. And so we want to use this product to make CC of G into an algebra. And this is achieved using the convolution product. Okay, so suppose that G is ample, and take phi and psi in CCG, then the convolution is again a function which, when applied to an element G in G, is the sum over all pairs ST of composable arrows in G, whose composition is exactly G, of phi s times psi t. Okay? So I defined this, the value of this composition, of this convolution, as a sum of elements. All of these are elements in K because phi and psi take values in K. So for this to make sense, I should show that this sum is finite, right? But it is enough to show that the convolution of the characteristic functions of two cops is well defined, because then by distributivity, I get good definition for everything, because I'm using this proposition. So I just need to worry about the characteristic functions of the cops. Now, if U and B are cops, then one checks that the characteristic function of U convolution, the characteristic function of B, is the characteristic function of U composed with B, which we said last time that is again a cop. Okay? Right. And so we extend by bilinearity and bilinearity, and then AKG is CCG, the K module CCG equipped with this convolution product. This is the Steinberg algebra. This was defined simultaneously in one paper by Ben Steinberg and another paper by Lisa Clark and other co-authors. But it was these co-authors that championed the name Steinberg algebra for this algebra. Okay, because Steinberg is perhaps the one that proved the most fundamental basic results on the subject. Okay, so right, I want to compare this algebra with another algebra, which is the semigroup algebra. Okay, so whenever there is, as we learned, whenever there is an étale groupoid, there is a semigroup lurking behind. And yeah. So, by the way, in this proposition I just erased, I forgot to make a remark. In the proposition, we may replace the whole semigroup of cops by the subsemigroup S, such that that is closed under the operations that we had there. Okay, such that these things are again in S for every V1 Vn in S, and these things oh. Okay, and so this S, typically we have a semigroup S acting on a space X, and the cops that we consider are these ones. Okay, so if these satisfy this hypothesis, we say that the action is Boolean. Okay. So semigroup algebra. We have appointed semigroup S and K as before. And we do the following. We define Ks to be the free K module on all non-zero elements of S, and to make this into, which we will make this into an algebra using the product of S, of big S. Now, what happens if S and T, I multiply them and I get 0, the 0 of S? This is not in the list. So I want that to be defined as 0, the 0 of this K module. One way of saying that is, well, I take the sum of the Ks for all S in S, which is an algebra with the product of S, but then in this algebra, there will be the 0 of S and the 0 of the K module. So to make these two zeros one and the same, I just divide by the multiples of 0, 0, the 0 of S. Okay? All right. So this semigroup has the property this semigroup algebra has the property that to give, so say I is an algebra, and well, phi is the K algebra homomorphism. Then I can restrict phi to S, and I get the map from S to A, which I can regard as a semigroup, pointed semigroup. And this is a homomorphism of pointed semigroups. Conversely, if I have a homomorphism of pointing semigroups, one of these, then I can define phi of the sum of A of lambda S times S as the sum of lambda S times phi of S, psi of S, and this is an algebra homomorphism. Okay, so what relevance does this have? Well, we know that we said before that the compact open subsets, the compact open bisections of an ample groupoid generated as a K module. So a corollary of that proposition is that K of the compact open bisections, so we have the natural algebra homomorphism from here to AKG that sends U to the characteristic function of U. Mapping U to the characteristic function of U is a semigroup homomorphism. Why? Because the characteristic function of U composed with B is exactly the convolution product of characteristic function of U and characteristic function of B. So therefore, this induces a homomorphism, and this homomorphism is surjective. Why? Because the COPs the characteristic functions of COPs generate this as a K module. Moreover, by the remark I said before, if G is S cross X and X, the action is Boolean, then K of S also maps surjectively onto the AKG. And the map sends S to the characteristic function of S, domain of S. Algebra, homomorphism. Okay, that's all for today. Yeah, that's all for today. Are there any questions? The problem in defining Steinberg algebra Well, for example, you want the characteristic function of an open bisection. Yeah. Sorry, the question, I had some question from the lecture room on what's the difficulty in defining the Steinberg algebra of an étal, not necessarily ample groupoid. Well, I mean, I would like that the that at least in the Hausdorff case, my functions be continuous. And the characteristic function of an open subset, which is not closed, is not continuous. And that will happen with arbitrary open bisections. So certainly, if the space is not weakly Boolean, then you only consider the characteristic functions of compact open subsets, then it's like you're changing the topology, or you're not considering the whole topology, something like that. So that's not the thing to do. You can define, for example, so in Excel's monograph, there is a definition of compactly supported continuous functions on an étal groupoid, which are not necessarily continuous. And they are functions whose support is contained in an open Hausdorff subset, not necessarily closed, and that are compactly supported inside of this open Hausdorff and continuous there. But if you, and in his case, he's considering functions to the complex numbers, where the complex numbers carry the usual Euclidean topology. You might think, well, I can take my favorite unital commutative ring and take continuous functions with the discrete topology and make the same definition, which is fine, but in the ample case, you do not get the same thing. You do not get the Steinberg algebra. Because all the functions in Excel's algebra have the interior of their support is always open. And as we've seen, this is not the case in the Steinberg algebra. So, you're welcome. Okay, so if there are no more further questions, I will stop the recording. Stop the recording.
Okay.